okay, right? And what you're supposed to do is to work on inhomogeneous magnetic fields. Okay, next, Cat A problem again, the latent frost stars. Okay, this again, right? There are, it's an old subject. There are many papers. Okay, so what is new? Okay, right. So let me read the question, the problem statement first. Right, in latent frost effect, right, a water drop placed on a hot surface. Right, this surface has to be hotter. Right, how hot? Has to be a few times the boiling point of water. Okay, right, and can survive for minutes. Okay, so if you drop water, right, to a hot pan, right, that is let's say close to the boiling point of water, right, the water will just vaporize. Okay, but when the surface is super hot, okay, very hot, okay, right, much hotter, much higher temperature than the boiling point of water, then you will notice that the water drop actually survives. Okay, right, and right, so the new thing is, under certain circumstances, right, such a drop develops oscillating star shapes. Okay, right. So your job is to induce different oscillatory modes and investigate them. Okay, right. So basic theory that we all know, okay, or you can easily imagine, is that when you have very hot surface here, when you put a liquid drop onto the surface, what's going to happen? Because of the very high temperature gradient. Okay, very high temperature gradient. Okay, is going to cause the surface vapor here on the drop to vaporize. Okay, so when it vaporizes, it forms a vapor layer. This vapor layer is insulating, right, and is supporting the water droplet on top. Okay, so that's how the water drop can survive for minutes. Yeah. Okay. Right. So in this case here, we can see from this picture, right, that the weight of the droplet would have an effect. Okay, because that will determine the rate at which the vapor leaves, right, this space between the vapor and the hot surface. And heat gradients or temperature gradients, okay, and vapor flow will be important factors in this thing here. Okay, so I'll show you the video of what we mean by oscillatory modes. Okay, so a suggestion, how do you do this? Oh, just now that one was not impressive. Okay, so these are the star-shaped oscillations. Again, if you look at the literature, this is not new, as in you can have papers as far back as 1952, right? That talks about vibrations of latent frost drops. Okay, so you may wonder, then what is new? Right? So let me highlight the statement to you. Okay. So what is new? It's not you produce a drop, right? Because listen carefully, not after you create the drops, okay, which is actually not difficult. If you have a curved hot surface, right, you just put a drop there, right, and then remember, if it's hot enough, there will be a layer of vapor formed, right? So your drop will be stable, rather, okay, right? So one way you can do is that you can change the mass of the drop even by taking a drop, something, and then you just drop or introduce more water into the drop, okay, with a dropper, okay, right? And if you disturb the drop, of course the drop is going to oscillate. Okay, but that oscillation is not the oscillation that you're supposed to study. Okay, the origin of the pressure oscillations observed in our experiment remains unclear. The pressure oscillations is actually because for this group of people, right? I don't know where they're going to find a pressure sensor and attach it at the bottom of the hot plate. Okay, right? So they actually measure the pressure oscillations due to the oscillations of the water drop. Okay, right? So if you actually read into this and some other papers, okay, what is new is this: if you have a drop, okay, you introduce a drop, it is not going to, it's not going to have any motion, but after a while, it starts to oscillate on its own, seemingly on its own. Okay, right? So if you have been looking at instability on the surface of water drops and so on, then you may not be surprised. Okay, but that is just a guess that what is actually going on here. Okay, so surface instability. Okay, right? But the important thing, of course, is to actually create experiments that demonstrate that this is the case. Okay? Among all this experimental theory, there is one, among all these experimental papers, there is one theory paper, and this seems to be the only theory in the market, but nobody cares. Okay? Yeah, right, so this is the only available theory. Okay, so I suppose you need to work on the theory, modify it, okay, accordingly. Okay? Right, so Cat A, okay, Cat B problem seems more interesting. Okay. Right, so this one, this is the picture that were taken for all the different modes of vibrations. Okay, one key thing is actually droplet size. So that's why I said that you have to think about how you can introduce a drop and how you can actually change the size of the drop. Okay, remember in this case here, evaporation rate is going to be very high. Okay, so your drop, even though you can survive for minutes, it's just minutes. Okay. Right. So two monstrous problems for Cat A. So I'll give you an easier problem now. Okay. So fast chain. You have a chain consisting of wooden blocks inclined relative to the vertical and connected by two tracks. See figure, which is here. Right, it's suspended vertically and then released. Compared to free fall, the chain falls faster when it is dropped onto a horizontal surface. Explain this phenomenon, okay, right, and investigate how relevant parameters affect the motion. So I'll give you a video first. Right, so the chain that hits the table, right, obviously is being pulled down, okay, and so it can move, actually can fall down faster than G, okay, as demonstrated in this video here. Okay, so this is real, right? Now, before I go away from this video, you notice this experiment is in a mass, right? Where's the mass? MESS. Here. Okay, right? So, so the theory that you're going to see is going to be an ideal theory that assumes none of this thing happen. Okay, right? So therefore, obviously, you're going to have deviations from your experimental data that you have collected and the theory. Okay, but then of course you can work on the other side, that is to actually improve on this situation, right? Avoid this thing from happening. Is it possible? I don't know. Okay, so there are things to work on. Okay, now when it comes to chain, well, you have some pretty standard analysis, okay, right? So this may start you off thinking about the problem, okay? And you can see here in these pictures, right, when you design experiments, okay, when you design experiments, there are so much details that you have to take care of. This mechanisms here, these pieces here, right, is just to make sure that you have something that can drop both chain at the same time. Okay, right, so, well, okay, so some standard analysis that you can, right, that you can find in actually standard textbooks, right, I presented here. You can work through it yourself, right, and so that you can understand better what the paper is trying to tell us. Okay, essentially has to do with this N2, okay, this force, okay, right. This force is the one that if it is present in this form and N2 is positive, then it will actually pull the chain down, okay, right. So going through this analysis, well, if N2 is 0, we actually get the so-called classic, result that most textbooks will present. Okay, but however, in general, N2 need not be 0, and you could design a chain such that N2 is positive, which you have seen just now. Okay, so this problem is about this chain. Okay, it's about this chain. Okay, so if you try to understand how come this chain obviously has a sucking effect. Yeah, you can pull down. Okay, it has to do with the way we arrange the rods. Okay, right. You notice that the rods are arranged in a special way. Okay, right. And what did I do here? Oh, nothing. Okay, right. I mean, you can read it on your own. I'm going to work through all the maths with you. Okay, so this is another standard example in textbooks. Okay, right. Which actually demonstrate what. That a rigid rod, okay, when it falls, okay, it can actually fall faster than g, okay, right? So if we actually take the Newton's second law and try to solve this, I guess you can't do it by hand, so I do it numerically. You can see that, right, at some point in time, right, the acceleration of the rod will be higher than 10 meters per second squared, okay, yeah, right? So yeah, so that is the basic thing that if you ask for a reason how come the chain can fall faster than g. Oops, where's my picture? Oh, it's gone. Okay, right. It has to do with the way it is arranged. Okay, right. Okay, right. So I have a few more things that is from the paper. Right, because from the paper there are some results that I feel I need to crack it before I present it to you, so I crack it, and then after you crack it, usually there's nothing much. So, I hope these few things that I fill in will help you to digest the paper more easily, okay? Right, yeah, be mindful, just be careful. This slide 22, just like in the paper, this is considering this is not actually considering the chain. It's just considering, okay, if I have a rod, right, that is inclined at a certain angle to the horizontal and it hits the ground, okay, what happened? Okay, in terms of angular momentum, in terms of linear momentum, okay, right? But this exercise will tell you how to deal with the case when you have whole chain of rods up there, how to analyze it. You actually analyze it, in the same fashion. Okay, so don't get confused. This result is not to be applied to the chain. It's just applied to one rod that is not connected to anything. Okay, right? And then you apply the same idea to analyze it in the situation when there's a chain of rocks on top of this particular one. Okay? Right? Use the same basic ideas, you will arrive at this interesting result. The impulse, right, I1, that means the first time the rock hits is 1/3 mv. Okay, when the chain of rocks come down with velocity v. I2 is 1/6 mv, and I3 is half mv. Okay, the final impulse that stops the rock. Okay, right, so these numbers are so nice, right? Okay, right, so that's the reason why I said I have to work through it, and it makes sense. Okay, right. So that's cat A, the so-called easier problem. And for this problem, you only have one paper to read. Okay? Right. So I'll say this problem is one that we should complete it. Yeah. Okay, next. Another monster problem. Cat A, spiral waves and other types of wave patterns, right, may occur on a thin liquid film flowing over a rotating disc. Sounds familiar? Rotating disc. But this time round, you don't put a ball on it, but you put water on it. Okay, investigate these wave patterns. Now, experimental setting, okay, bear in mind, there are two possible and could give rise to quite different results kind of setup. Namely has to do with the way you introduce the water. So you can have a rotating disc, okay, you can introduce a pipe vertically from top, okay, and then you introduce the water. Okay, another way, not from on top, cannot go sideways, so we go from bottom, below. Okay, right? So you have to think about how you're going to do the piping. Okay, so water will flow from below, water will flow, right? Just like, right, you have an opening, then the water just flow out of the opening. Okay, right, for water on top, okay, right? I think that one is easier to imagine. Okay, so what's the difference between the two? Still remember light rings? Water on top, right, is going to create a stress, okay, right? So there's one paper that I'll give you that actually believes that is the main thing that gives rise to the wave pattern, okay, the instabilities on the surface, okay, right? But of course, there are people who believe otherwise, okay, that there are other reasons why you have these instabilities, okay, right? And of course, if you have water coming from below, then you may have that. You may remove that problem. Okay, right.